Stefano, we can start.
Okay. Thank you for being here for the third lecture. So I will briefly recall what we did yesterday. Yesterday I showed explicitly by solving the Capel model and the Kardashev model in the microcanonical ensemble, how ensemble inequivalence shows up in the phase diagram, in the sense that the transition lines do not agree, and mainly the fact that the second order transition line extends beyond the canonical one to reach a new point which appears in the microcanonical ensemble, which is we have called microcanonical tricritical point. And that's an interesting point also from the point of view of dynamics, because I have shown, for instance, that there is a new kind of metastability that appears in mean field long-range models, and also the fact that being temperature a modified, a derived quantity in the microcanonical ensemble, it can show bimodal distributions. And one student asked yesterday for the paper in which I show the distribution, and I have sent him the paper, so he should have received it. So it was the plan yesterday to, as usual, I have to stop sharing and then sharing again. Let me see. Screen. Yes. Okay, I promised yesterday to talk about the method. So the lesson of today is essentially devoted to improved methods to get the microcanonical solutions, in particular this min-max method and the large deviation methods. That were already present in my review of 2009, but there have been developments, and this is a very nice book edited by Angelo Vulpiani and co-workers on large deviations in physics, where I sort of collected all the type of results that we get using large deviations. So since I have many topics to cover today, I will try to be a little bit faster than in previous lectures, but please, if you really feel that I should slow down, tell me, okay? Because I would like today to talk about these two methods and how these are used to solve the three-state post model, and also some XY model and the model of free electron lasers, and a mean field 5-4 model. Okay, so, for the tutorial today, I hope I will have time. I will comment about the law of large numbers and the central limit theorem in the light of large deviations, in particular in relation with the solution of models with long-range interactions, and how, for instance, coin tossing is related with the entropy of the Ising model. And then I will give, if I will have time, just a sketch of the derivation of the solution of the model that I mentioned in the first lecture, the Hamiltonian mean-field model, in both the canonical and the microcanonical ensemble. Nowadays, we can solve this model. And as in the tutorial, I suggested to, in some sense, to prove equivalence for the Curie-Weiss model. The equivalence of the proof of equivalence for this model is slightly more complicated, but it requires some more effort, but it can be done. Okay, so I hope that I will cover most of what okay, so let us begin with this min-max method. So what's the idea? The idea is the following.
Hello?
Can you hear?
Yes. Before you start, can I ask a question?
Sure.
In real experimental systems, like how do you see these inequivalence of ensembles?
Yes, first of all, I must forgive for not having clear experimental evidences of the ensemble inequivalence. So there have appeared some even experimental papers claiming the presence of negative specific heat, for instance, in the cold atoms experiments. But I must say that the evidence is not very convincing. Essentially, the point is the experimental condition should be the same of the ensemble in which you make the derivation. So suppose you want to check a prediction of the microcanonical ensemble, so the system should be isolated. Okay, this is so it should not exchange energy with the environment, and the energy should be constant. And then you will find that the prediction of the microcanonical ensemble. If you want instead to have to see the results in the canonical ensemble, you simply put the system in contact with the heat bath. You carefully check that it is in equilibrium with the bath, and then you will have the energy will fluctuate according to the canonical ensemble. So it is really the experimental conditions that matter, so that you are able to. Now, of course, they will never be perfect. No, you will never be sure that there is not a slight leak in energy, or that the thermostat is not very well in equilibrium with the system. But this is a type of experiments that should be done. Is it clear, my answer?
Yes.
But if it's not, you can also. I mean, it's a difficult issue because so for instance, you could observe negative specific heat, but you don't really know whether you are really in equilibrium, if it is an equilibrium observation or not. For instance, this is a type of question which remain open. But overall, I must say that the weakness of the field is very much related to the fact that there is no clear experiment showing this. Now, there are other types of ensemble inequivalences. For instance, there are other types of ensembles. So there is the grand canonical ensemble, the isothermal and constant pressure ensemble. So one could play also with these other ensembles, and similar types of inequivalences appear. So the panorama is in fact much broader. Okay, so let's start with this first method. It's called the min-max method. And okay, so what is this method? The method is based on the fact, on a hypothesis, that you can write the partition sum as a function of beta and n, the number of particles, as the integral over a dummy variable x times the exponential of minus n times a function u, which is a function of beta and x. Now, this is a strong hypothesis, but we know that that this exactly this form of, and I will show an example of representation of the partition sum is generated by the Hubbard-Stratonovich transformation. Okay, so given this form, it is clear that the Massier potential, so the inverse temperature times the free energy as a function of beta, is the infimum over x of the function u that appears in the numerator. So in the exponential inside the integral. So it is clear that okay, you have already access to the free energy. So there is that's a direct. So the question is, do we have access to the entropy given by you can get this representation. So let us introduce the Legendre-Fenchel transform of U, which is our extended free energy, let's say, because it is not the free energy in terms of beta, but is a generalized, if you want, is the Landau free energy, which is also a function of the dummy variable x. So let us define an entropy, which is a function not only of energy as usual, but also of the dummy variable that appears in the representation of the partition sum. So the Legendre-Fenchel transform is is obtained by taking the infimum of beta epsilon minus u. Okay, the proof is slightly complicated, so I would like just to state the result. The proof can be done either by standard saddle point methods or can be done using the large deviations. The second proof was given by Ugo Touchette. Okay, so how do you get the entropy? You get the entropy is if instead of computing before the infimum of over x of the function u of the generalized Landau free energy, u of beta and x, you first compute the infimum over beta, and then you take the sup over x. Clearly, the infimum over beta is our generalized entropy, S of epsilon and x. So in order, you have to take first the Legendre-Fenchel transform of the Landau free energy, and then you have to take the sup over the supremum over the dummy variable x. What essentially you are doing an inversion of two optimizers. Instead of taking first the infimum over beta and then the supremum over x, if you had taken first the supremum over x and then the infimum over beta, you would have gotten the Legendre-Fenchel transform of the free energy, beta. So you would have gotten what could be called the canonical entropy. So in some sense, so the convex envelope of the microcanonical entropy. Okay, the proof requires a little bit playing with sup and inf, in particular with the fact that if you invert the sup with the inf, so if you take the in the order inf and then sup, you get a quantity which is smaller or equal than the sup, then taking first the sup. Okay, so let us show a result. So the model is very similar to the one of that I've shown with Kardashev in the solution of Kardashev, but it's an XY model. So now we are in one dimension. Okay, you take a term which is a sum of cosine of difference in angles. Okay, this is the local term, the analogous of the sigma I plus 1 in the Kardashev model. And then you have the usual mean field Curie-Weiss term. So you have the sum over all pairs I and j of theta I and theta j. Now, if you write the cosine of theta I minus theta j as a square, you can always do it because the cosine of theta I minus theta j is cosine of theta I cosine theta j plus sine theta I sine theta j. So you can, by two Hubbard-Stratonovich transformation, you can write this part of the partition sum as a linearized term, which is this sum of cosine theta. And here I've already done a step in which instead of using two dummy variables, I use only one, using essentially rotational invariance. So you can convince yourself that this is plausible because you can rotate the angles in such a way that this term, the sine term, does not appear in the calculation. So then you get the partition sum as in the form that I was telling before. So this is, in particular, this is the u function that I was defined before. Now, the integral over theta is not, of course, straightforward. And in fact, it cannot be exactly done. By the way, this is a problem that maybe some of the students is interested in calculating exactly. So I didn't succeed to solve this transfer matrix. So having a system where two nearest neighbors are coupled, it is very natural to introduce the operator T, which acts in the space of functions of theta in this way. Okay, integral of the alpha of so the operator is symmetrized in alpha and beta in order to get real eigenvalues, and so you have to find eigenvalues and eigenfunctions of this operator, and unfortunately the solution is not possible analytically. So either you can solve it for the local case or for the non-local case, but if the two terms, the local one and the non-local one, are present at the same time, there is not an explicit formula of the maximal eigenvalue. Are there questions? Hello?
Yes. How did you get partition function in the second line? Is it like
how do you get
partition function in the second line?
The function in the second line is obtained using the same transformation that I used in the tutorial to solve the Curie-Weiss model. It is a bit more complicated because you need two dummy variables, but then using rotational invariance you can eliminate one of the dummy variables. It requires some calculation, so it's not straightforward. But anyway, I can just point out that this term, you see z square, is very similar to the term x square that I showed in the Curie-Weiss calculation. And the z times sum of cosine is very similar to the term sum over the external field, no? The external field term that you have in the Curie-Weiss. And this is just this term, the beta k cosine theta is just copied from here, no? So essentially you see that it has the structure of the Hubbard-Stratonovich transformation of the Curie-Weiss model. But it requires some steps, intermediate steps. I have preferred to give a clear formula without giving all the derivations, so that you can I can also point out what are open problems. So for instance, in this case, the open problem is to compute eigenvalues and eigenfunctions of the operator that I call T analytically. I think it's possible, but I could not do it. So I could do it in some limit. For instance, I could do it in the limit where K is small okay, but it's not very helpful. So then you can resort, of course, to numerics, and you can get the numerical eigenvalue. Then the partition sum is this integral of z dz exponential of this function, where the maximal eigenvalue lambda, which is a function of beta z and beta k, is a function, of course, of z, and then one has to perform a saddle point to get, for instance, the infimum to get the free energy. This is what you would usually do. You take I don't remember now either the sup or the, if you take the inf, yes, in z, the inf in z of the infimum in z of this expression, you get the free energy. But as I was saying, if instead of taking the infimum in z, you take the infimum in beta of the Legendre transform of this, and then you take the sup in z, you get the canonical, the microcanonical entropy. So the entropy as a function of energy, which is very useful, because in order to count the states in this model, you would have to solve the problem of counting in a continuum, no? Because you have a continuum of values of theta. So this method avoids doing direct counting. In a recent paper in JSTAT-FIS, we have generalized the method, and we have shown that the method can be used also to compute the entropy as a function of energy and of another, for instance, conserved quantity. So for instance, you could take the magnetization, and you could try to solve the problem of computing the entropy as a function of energy and of magnetization. And it works, so it's an interesting method. Of course, there is a very strong hypothesis. The strong hypothesis is that you can write a partition sum in this form, which is the case for this model. Okay, and what you get, unfortunately, oh, I forgot to put a slide. Okay, what you get if you study the phase diagram of this model, now that you have, are there questions?
Hello.
Hello, are there questions?
In the second line, is the sum there?
In the second line, here.
The last term, there is a sum, right? Sum over I.
In this line, sorry, I cannot hear well.
Hello, can you hear me?
I didn't hear well. So, which was the question?
No, so Stefano, the question is, I think, like, since you have a product over I, so you shouldn't have the sum inside, I guess.
Ah, yeah. Sure. Sorry. This is just. Sorry, this is a notation which is not. So this is just. You have to trace over all thetas. You have to trace over all theta variables. Okay, so you have to take the integral over all the thetas, over all the configurations of the theta. This is a sloppy notation, sorry. Okay. So I would replace this by tracing over configurations in theta. Okay. So maybe, okay, I should have added a slide, but otherwise I would not have time. But the phase diagram of this model is very much the same of the one of the Kardar-Nagel model. So it displays the same phase diagram for negative k. For negative k, you have microcanonical and canonical tricritical point, and it is essentially the same phase diagram as the Kardar-Nagel model. Okay, so this is finishes. Okay, so I'm hearing some noises. I don't know if you also hear. Okay. So, but please don't hesitate to put questions. Yes, this slide I was very fast in preparing it, so I did some small mistakes. Sorry?
The question. So, I mean, so in this case, there's no inequivalence of ensembles, or?
No, there is an equivalence of ensembles. I'm sorry that I don't have I have cut out the slide to reduce them. There is an equivalence of ensemble, and this is exactly the same inequivalence that you find in the Kardar-Nagel model. Exactly the same. So in the negative k, the phase diagram will be different in the two ensembles, and we can compute both the microcanonical and canonical tricritical points. They do not coincide, and they show very similar. So essentially, this XY model is very similar to an Ising model. It's more, so for us, it was a challenge, because while in the Kardar-Nagel model, it is possible to perform the calculation of the entropy directly, it was not clear how to perform the computation of the entropy in a case in which the variables are continuous. So the challenge was this one for this model. We expected to have ensemble inequivalence, but we were not sure until we were able to compute the entropy. So I'm sure that the final expression for the entropy is the one on the bottom, or the last formula in this slide. Okay. So, and then analyzing this entropy, which is not easy, because you see that you have to take to solve two variational problems with a quantity lambda that you know only numerically, but everything can be done, and you get ensemble inequivalence for in the negative k region. Okay, let us now remind an important result in large deviation theory, which is the only one I will use. In fact, in the field of long-range interaction, there are many results of large deviation theory that can be used. And this is the result due to Cramer. So let's state the theorem. So let X be a random variable with given PDF in RD. So R is a vector, X is a vector, sorry, a vector of in RD in dimension D. And then let's take a sample of these random variables. So I extract a sample of n of such random variables, of such vectors, and then I take the average of that. Sorry, just a minute. Prella. Okay. Okay. Okay, ciao. Sorry, but it was an urgent information I had to catch. There is a fire near where I'm giving the lecture. So, but everything is fine. I can go home by the standard. So, unfortunately, we are experiencing climatic change, and even in Italy. So there's been a big fire near Trieste. You can look at the newspapers. It is also mentioned in on the national newspapers. So, but everything is fine. I will go on. Okay, so let's take a sample of this vector, which means I take the average, finite n average. Okay. And the question that the Cramer solved for IID random variables is the following, which is the probability distribution function of the sample mean. So so xi is a random variable. A sample mean is a random variable. So what is the distribution of the mean of the sample variable of the sample, so-called sample mean? Okay. And the way to get so the Cramer theorem is not only a statement about the properties of such a distribution, but is really a concrete result which allows you to compute the probability distribution. So you have to do the following, is a recipe. Okay, you have first to take the average over the distribution of the variables of the exponential of lambda, which is also a vector, times x. Okay, so you have the local random variable x, you multiply by lambda, scalar product, then you take the average over the distribution. Lambda is, of course, a vector in RD, and the average is performed on the PDF of x. Now, if psi of lambda is finite and differentiable, these are the two strong hypotheses of the theorem, then the probability distribution of the sample mean, so the probability that the sample mean Mn is equal to x, is proportional. It means proportional means apart from corrections that go to 0 if you take the log, okay? Sometimes mathematicians say it's logarithmically equivalent to exponential of minus n times I of x, where x is called the rate function, and the rate function is given by Legendre-Frenchel transform of log of psi of lambda. Okay, so it doesn't require other properties of psi of lambda, and so you get directly the rate function using this trick. Is it clear? I don't hear. Are there questions on that? No? Okay, maybe this theorem is already well known and has been used in many results from meanwhile. At the time when we were first using this result, for us was a real true discovery, because it opened us the way to solve many models. Even both the Blume-Capell model and the Kardashev model can be solved using this method that I will describe to you. Unfortunately, we have not published this result because we have solved the models in the other way. But it is really a very powerful method. So it allows to solve many different models with long-range interactions. So what you have to do, you have to work in 3 steps. I will describe the step, and then I will describe the solution of the 3-state mean field Potts model using the method. Okay, so you have to express the Hamiltonian in terms of what can be called global variables, which are in some sense mean field. So as you know, the Hamiltonian Hn is a function of the phase space, no? So omega n is a phase space configuration, okay? You have to rewrite the Hamiltonian as a sum of two terms. In the first term, the Hamiltonian depends on the global variables, which are functions of the phase space, of the phase configuration. The second term is a rest, so is what remains after having expressed the Hamiltonian through the, which you have to prove that goes to 0 as n goes to infinity. Okay, it should not be 0. You will see that in the case of the Potts model, it is exactly 0 because it's a mean field model. But it can be also a rest that you can prove that it is going to 0 as n goes to infinity. Then the second step, you have to compute the entropy functional in terms of the global variables gamma using, for instance, Cramer theorem. I will show you what I mean. So essentially, you have to compute not the configurations that are compatible with a given energy, but you have to compute the configurations, the volume of the configurations, which are compatible with a given gamma or set of gamma. So it can be, the set of gamma can be as large as you want, is a vector, but it should not be the same size of the system size. So should not be as big as n. Okay, so the set of gamma, otherwise it's not manageable. Okay, so in some sense you are reducing the complexity of the configuration to a set of finite global variables, and you are trying to compute the volume compatible with a given value of this set of global variables. And it is in this step that you use the Cramer's theorem. So to get this S of gamma, as I call it, so the volume corresponding, the log of the volume corresponding to a set of variable gamma. Then you can solve both the microcanonical and the canonical variational problem. So to get the entropy as in the microcanonical ensemble, you take the sup over at fixed energy. So h of gamma is the limit of hn tilde in the limit where n goes to infinity. So you take the sup of S and you get the microcanonical entropy. So similar to what I did when I solved both the models yesterday, you can express if you can express the global variables in terms of the energy, you can maximize over all the global variables at fixed energy. And the other, the canonical ensemble you get, so the Massier potential beta f of beta, you get by taking the infimum of beta h of gamma minus s of gamma. So you have really two independent ways of solving the system in both the canonical and the microcanonical ensemble. And you also can clearly see from this expression that it is really reasonable to expect that the two variational problems do not have the same solution. Okay, so that the ensemble equivalence should be in fact proven. Okay, so this is the thing that I then. Okay, I will illustrate it on a simple example. I have tutorials where I showed how to use this method for the Kardar-Nagel, for the Blume-Capell. So there are many models to which this can be applied. But this is really the simplest case. So the model is the POTS model in with 3 states, A, B, and C. So in the POTS model with mean field POTS model with 3 states, you have a sort of Curie-Weiss Hamiltonian, and the step 1 is trivial in some sense because the Hamiltonian Hn in the H tilde n in this case coincide with Hamiltonian Hn. So it's because the rest is 0. Okay, so you can write the Hamiltonian in terms of 3 global variables: the number of A states, the number square, the number of B states square, and the number of C states square. Is there a question? Is there a question? No, okay.
I think no.
Okay. Okay, then the step 2 is performing performing the volume calculation. So you have first to realize which is the fluctuating variable. The fluctuating variable is the sum over the spins that are A, the sum over the spins that are B, and the sum over the spins that are C. Okay. And the local random variables is the delta of Sk. So this is local random variable, means that either the spin Sk is A, or is B, or is C, but it can be B, C, or A independently. So there can be a 1 here, 0, 0, or it can be a 1 here, 0, 0, and so on. Now, the generating function, the one that is defined in the can be easily computed in this case because you sum over the 3 variables A, B, and C the exponential of lambda times the local variable, so of the product of the delta, and you get 1/3 of e to the lambda A, e to the lambda B, e to the lambda C. The rate function is just the sup of lambda A and A, lambda B and B plus lambda C and C minus the log of psi, which psi has this form. The exact solution of this variational problem tells you that lambda L for L equal A, B, C is the logarithm of NL. This is easily done. So you substitute back and you get the maximum. Then the entropy, which is minus the rate function, is expressed by the function I of gamma. Then, of course, I have to solve the variational problem by taking the sup over the sum of NA and B and NC should be the total number of spins. So if it's normalized to n, the sum should be 1. You see that here appears NC, which is 1 minus NA minus NB. This is the energy. And you have to take the sup over NA and NP of this quantity. For the canonical free energy, instead you have to take the inf. Okay, now I describe now the same thing that I asked the students to compute for the Curie-Weiss Hamiltonian. For the Curie-Weiss Hamiltonian, I asked the students to plot beta, or the inverse of beta, as a function of the energy. As for the Curie-Weiss model, there is a maximal energy in this model. So there are no states above the energy -1/6. For the Curie-Weiss, it was the energy 0, okay? But the formula for the Curie-Weiss essentially was a function. If the student has computed it, I've shown the result to the students yesterday. The beta is a function which diverges near the ground state energy, and then and then reaches some value here at the largest value of the energy. While in the Potts model, if one solve this variational problem, instead of finding the function that starts here very high and then reaches some value, a simple function, of course, if you plot 1 over beta, you get a function which is 0 on the ground state, the temperature is 0 on the ground state, and then reaches some value at the upper boundary for the Curie Weiss. Instead, you see here, for the Potts model, that beta, the inverse temperature, goes down, 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 down until here, and then it has a minimum. And then it starts to grow. So if beta grows, means that beta, which is the inverse temperature, beta is the inverse temperature, decreases as the energy increases. So this is a negative specific heat branch. Here you see. Beta is a continuous function of the energy in the microcanonical ensemble. There is no phase transition in the microcanonical ensemble, but there is a negative specific heat. So it means that the entropy, I've not drawn the entropy, but it's easy to draw. It means that the entropy is concave here, but it is convex here, okay? Because you get a negative specific heat. Instead, if you solve the model, so there is in this case, no phase transition in the microcanonical ensemble for the Potts model, for the 3 states Potts model. Instead, if you solve the model in the canonical ensemble, so you solve this infimum problem here, what you get, of course, now you have as a free parameter, you have beta. So you have to increase beta and compute the energy by using the formula derivative of beta times the free energy with respect to beta, okay? So the energy is flat initially in the canonical ensemble until you reach a value beta of the transition beta, where you have a jump in energy. So you have a typical signature of a first order phase transition, and then the energy grows again, okay, as beta grows. So you understand, instead of plotting beta as a function of the energy, I plot energy as a function of beta. For the Curie Weiss, if you have done the exercise, you would have found the same. So the 2 functions are the same function. Here, I get 2 different functions. So beta as a function of epsilon is not epsilon as a function of beta. While in the microcanonical ensemble, I have no phase transition and the negative specific heat, in the canonical ensemble, I have a first order phase transition, and I have a latent heat at the first order phase transition. And if you do the calculation, you will discover that these 2 areas here, this area here, and the area of this set here, they are the same. So you have the usual Maxwell construction in this very, very simple model. But you already see that the effect of non-additivity shows up in this model, and you get an inequivalence in such a simple model. I think this is really something that could be done in a lecture course, in any lecture course of statistical mechanics, because it's a very simple example of ensemble inequivalence. Okay, so are there questions?
No questions.
No questions, okay. So I think it's clear now that the origin of ensemble inequivalence, which has to do with the fact that the 2 ensembles solve 2 different variational problems. Now I will be very, very fast in this part because we are already done almost. So we have 40 minutes left. So yes.
The second term that you have written down in this HXY model, this is a simplified version of the other one that you wrote down, right?
This one that I'm showing now.
Yeah, there was another one that you wrote down earlier, right? In terms
At the
of
beginning, yes. That was different because you see it has a local term, no? Here there is a local term. It's cosine of theta I plus 1 minus theta I, like in the Kardar-Nagel.
Right.
Now I'm writing a slightly different model, which is inspired by a model of liquid crystals. It's called I don't remember the name. It's a model of liquid crystal. So in this model, I have it's the Hamiltonian. There is a kinetic energy. There is a sum of SI square, and then there is a sum of square of SI square. So I have a quartic term. Okay. So the model with the sum of SI square is so-called sorry?
To the power 3, I mean, why we are having that?
Why there is 3 here? Because this is the Katz term, the Katz factor for this term in the Hamiltonian. Because you see that I have a sum square square, so this term goes like n to the 4. So in order to have an energy density, I need to divide by n cube. Is it clear?
Yeah, thank you.
This is like it's like the Katz term. In this case, it's simply n because here I have the sum of n to the square, so this goes like square. I divide by n, I get something that goes like n. So in this way, all the terms in this Hamiltonian are proportional to n, so they are extensive. Okay. So the real issue here is that the model is extensive, but is non-additive. If you see the model as particles, it represents particles on a circle. And then in the broken phase, the particles accumulate somewhere on the circle, while in the paramagnetic phase, the particles are distributed on the circle, and there is a critical energy at which there is a phase transition. Okay, it looks like a complicated model, but in fact it is not, because as you can see directly from this Hamiltonian, there are 3 what I've called global variables. The one corresponding to kinetic energy, the one corresponding to the sum square, and the one corresponding. So and these are 2. There are 2 in fact, because then this is reduced to this one because it's a square of that. Okay, so finally there are 2 global variables. So then I can use the Cramer theorem because I can express the energy in this form. So kinetic energy plus m squared plus m4, and this is the local random variable. And then this model is in some sense the only difficulty present in this model. You have to understand how to compute the volume in the case in which there is a kinetic energy term, because it seems diverging the volume with kinetic energy. But in fact, you can put a cutoff and then do the calculation and then remove the cutoff at the end of the calculation. And what you get a psi lambda, which is this form here. It's the Bessel function, the modified Bessel function of 0 order function of the square root of lambda x squared plus lambda y squared divided the square root of minus lambda k. lambda k is negative definite, and then the rate function, which is minus the entropy, is obtained by taking the sup of this quantity here. And of course, the entropy then is obtained by taking the sup over gamma. It's a bit involved, but you get the solution in the microcanonical ensemble. And what you get is the following phase diagram, very similar to the one that, by the way, here I have a figure of the temperature jump with a finite n simulation, that one that I was mentioning yesterday, where you see the smoothing of the temperature jump. What happens here? It happens that for k equals 0, k is this coupling here. K is this coupling here. Okay, the coupling of the M4 term. So if k equals 0, I get a phase transition of second order at a value of p over j, which is 0.5. Then if I switch on k, I remain at this value for the phase transition. So the temperature is 0.5 until I reach a canonical tricritical point. And then at this canonical tricritical point starts a line of first order phase transition. That is the point, the dotted line that you see here. In the microcanonical ensemble, as usual, because this is a general result, the second order line extends beyond the canonical tricritical point and reaches the microcanonical tricritical point, where you have a branching of the two lines with the two bounding temperature. Okay, and here you can see that the 2 points, this is a comment of Abhishek. We were really not very lucky to start with the Blume-Capelle, where these 2 points were very close. Here, the 2 points are very far from each other, so you can see that they are very well distinct. And if you put yourself at a given value of k, which is the simulation, the representation I do here, I don't remember which value. It is maybe it's bigger than 5 over 2. I am in this part of the plot. 5 over 2 is 2.5, so it should be something here. Then I increase temperature, and I plot temperature as a function of energy. And then you can see that there is the full line is the analytical solution, and there is a negative specific heat region in this model. The experiment was done using molecular dynamics. So I solved the Hamiltonian equation of motion of this model, because I have a kinetic energy, so the true dynamics is given by the dynamics generated by the Hamiltonian. Here I don't have a problem on which is the real time. This is real time, not the Monte Carlo time. So you can see that you have a negative specific heat and then a temperature jump, and the jump is smoothed, is n, is finite. Here is a simulation done with 100 spins, 100 spins, yes. Okay, k over j is 10, k over j is 10. So I'm very, very far here. And you get this shape of the temperature energy relation, which is the one that you find typically in gravitational systems. Here there is nothing that reminds gravity. Okay. Okay, this is another model that we solved. In fact, it's an interesting model. It was introduced by Colson and Bonifacio, and it is a model which describes a process which is very important in application, which is the instability of light in a free electron laser. So I don't want to spend much time on that because it would require an introduction, but just to give a sketch of what happens. So in a free electron laser, by the way, there is a new one built near Trieste here. It's called Fermi. You have a gun of electrons, then you have an electron accelerator, so usually linear accelerator of electrons. And then the electrons enter in a region which is called the Wiggler, where there are alternating dipolar magnets. So here is south-north, this is north-south, this is south-north. Okay, so and if you look at the orbit of the electron orbit will wiggle, no? Because it turns when there is magnetic field and it goes straight when there is no magnetic field. And since in the next step the magnetic field is inverted, the wiggle is in the other direction. So the electrons trajectory wiggle in this way. And since they accelerate by the wiggling, they will emit light. The light interacts with the electrons. The model that you should start with is relativistic, of course, because the electrons have velocity close to velocity of light. And in fact, the variable P that you see here is in fact the relativistic kinetic energy minus the kinetic energy in the center of mass. So it's a complicated variable. But nevertheless, you have this set of three equations which are Hamiltonian. Now, you don't clearly see that they are Hamiltonian because there are three equations, so that you are not used to the fact that Hamiltonian models should have an even number of equations of motion. In this case, you have three. And the reason is that the variable A is conjugate A, which is the field. I have described here the field with only one wave, is conjugate to A star. So that's the reason why you get the three equations. Okay, so these are the three equations of motion of the free electron laser. So since we have this machine here in Trieste, I decided to solve this model. The Hamiltonian of the model is this one, okay, with kinetic energy. And A is the square root of A star. Okay, this is and okay, we get the entropy. I will go very fast here in terms of all the parameters. Okay, we solve the model. What we learn is that in this model there is a second order phase transition at this energy. Delta is called the detuning in the language of, and of course this phase transition is associated with the phenomenon that you see in the free electron laser. So essentially below a certain energy, there is no concentration of the electrons and no concentration of the light. And above a certain threshold, you have concentration of electrons and concentration of light. Here, for instance, I describe a simulation that we realized on the model. Z is the variable describing essentially the length of the free electron laser, so the length of the wiggling region, which is in fact time in some sense. Okay. And you can see here that initially I put myself in the region that is unstable, where the system tends to laser. And so you start, there is an exponential increase of the laser intensity, and then there is an overshoot, and then there are oscillations, and then there are oscillations, but you clearly see that there is an average here, okay? And this average is predicted by our theory. So we even tried to interact with the experimental groups here in Trieste to convince them that we were able to predict the length of the wiggler that would allow to obtain a certain laser intensity. but they were engineers. They were so worried about building the machines, they never gave us access to the machine, so it was impossible to do it. And meanwhile, they have constructed the laser. The laser works very well, so we are very happy that we didn't disturb them too much. So we checked the value on some other experiments done in other free electron laser machines, and the values are reasonable. So with because the model is Colson-Bonifacio model, the parameters are determined by fitting on other more complicated models. So they are not. It's a realistic model, so you can really hope to check the intensity of the laser. But one thing that appeared in this slide, and I will comment very briefly, it's important, is the following. You can see here in the inset the same as the main plot, but we reduced the number of particles. So in the simulation of curve 1, there are 5,000 particles, 5,000 electrons, okay? In the curve of figure 2, there are 400 electrons. And in the curve of figure 3, there are 100 electrons, okay? And you can see that the convergence of the one with 1,000 electrons is below the one with 400 electrons and below the one with 100 electrons. And you might wonder, what is the prediction of statistical mechanics? And the prediction of statistical mechanics is 3, which is quite amazing, because you would expect that predictions of statistical mechanics is better and better as you increase the size of the system. So what's going on here? It remained a mystery for a long time until we understood that the dynamics, in fact, is a solution of the Vlasov equation, and the prediction of the Vlasov equation is not the Boltzmann equilibrium, is another type of equilibrium, which is called the Vlasov equilibrium. And this opened the door to another important analysis that we have done in our group and also in the group of Jan Levin in Brazil, of the existence of quasi-stationary states in systems with long-range interactions. But this is just an opening a door, and but interesting to quote, because Nicolò De Feno will speak of similar effects observed in quantum systems. So these quasi-stationary states have a quantum counterpart. We first saw them in classical systems, but they have a quantum counterpart. Since it's already more than an hour that I speak, I would like to tell a joke about this result. We thought it was an important result, so we tried to publish it in Physical Review Letters. The paper was rejected and went to Physical Review E. So the reason why the paper was rejected is very interesting. It shows that when you work at some interdisciplinary project, you might have to fight with the referees. One of the referees was a plasma physicist and was telling us, the only equilibrium I am interested in is the equilibrium of Vlasov. Boltzmann equilibrium does not exist for me, because if I compute the length of a laser, a free electron laser that would converge to Boltzmann equilibrium, the laser should be 1 parsec. So should be an astronomical laser. While the statistical physicist, the one that was instead suggesting to publish the paper in PRL, was telling us, what is this strange thing as Vlasov equilibrium? I don't know any other equilibrium other than Boltzmann equilibrium. So since the two converged in saying that they didn't understand what we were doing, the paper was considered interesting by the editor, and because there was nothing wrong in the paper. So, and then went to physical review. This is just a joke that for the youngest people, that they will find themselves trying to publish things like that. Okay, so let's go to the next model, which is the mean field 5-4 model. So this is a mimic of the Ising model, but with continuous variables and Hamiltonian. So there is kinetic energy. The local potential is double well. And then you have a mean field term, which is 1/4n times n qi qj. These are real positions. It's a dynamical system with real positions. Also, in this case, there are global variables, u, z, and m. And then you can perform the calculation of the psi function, as we have done. In this case, it can be done exactly. And then compute the entropy and compute the entropy as a function also of magnetization. So you have everything here. So this is analogous to the Curie-Weiss model, if you want, because it's a sort of mean field with continuous variables. But since we have access to the entropy as a function of both the energy and magnetization, here for this model, we tried together with Ugo Touchet and with Alessandro Campa, we tried another response function. We wanted to compute, this is the entropy, is a function of epsilon and m. We wanted to compute the susceptibility. And what we found using the formulas of microcanonical ensemble, that the expression for susceptibility, which is this one, it is expressed, as I was mentioning yesterday, as through the Hessian of the entropy. So the entropy is now a function of both epsilon and m, and you can prove that you can write the susceptibility in this form: double derivative of entropy with respect to energy, then the mixed derivative square, and then the double derivative in both epsilon and m. Now, in the canonical ensemble, you can prove that, you know that S, the second derivative of S with respect to energy is positive, not because this is a specific heat, which is positive. The denominator is positive as a function of, as a consequence of stationarity. Hence, the chi, the susceptibility is positive in the canonical ensemble. Instead, in the microcanonical ensemble, both the second derivative with respect to n and the second derivative with respect to epsilon can be negative. And you cannot, therefore, you cannot prove that this quantity can be, is necessarily positive. And this is the result. You see that this is numerics, the points, and the lines are the result of the susceptibility. And you see that at a given value of m, the susceptibility becomes negative. It's not a surprise, because it's any response function. In this case, is the susceptibility, like the specific heat, can become negative in system with long-range interactions. Okay, conclusions. Large deviations are a powerful tool to derive microcanonical entropies. I have shown also the min-max method, which is another tool that can be used to derive microcanonical entropies. And also I've shown a list of models that could be enlarged, where using these two tools, it is possible to compute the entropy. So I would like to finish with the quote of Wang that I mentioned in the first lecture. So Wang says, there seems little hope that we can straightforwardly carry out the recipe of the microcanonical ensemble for any system but the ideal gas. This you find in the Wang book. I would like to contradict Wang in the sense that simply changing the sentence by saying that he is right, because the derivation of the microcanonical ensemble for something which is not the perfect ideal gas is not straightforward, but it can be done. Now, the type of questions that remain open, of course, are the hardest one. And in particular, I would like to point out that we know anything or very little about the models with decaying interactions. So the interaction that 1 over r to the alpha. So for this type of models, we mainly must rely on numerics. And it will be very important also for the quantum case, because Nicolò will talk about the quantum case, because as I told you in the first lecture, in the quantum case, it is possible to realize experimentally the varying exponents alpha from 0 essentially to any value you want to do in these cold ion experiments. So it will be very, very interesting, and I encourage the younger people to work in the problem with decaying interaction. Also analytically, it's tough, but it's very, very important to get results for this class of models. So the tutorial will be about, I will show, yesterday I showed the students how to do the transfer matrix for Kardashev. I will show the result, and also I will comment on the solution of the Hamiltonian mean field model in the canonical and microcanonical ensembles for the tutorial. So I finish here, and I leave the last 10 minutes for maybe for free discussion. I would like not to leave the impression that everything was done. It's absolutely not true. And there are plenty of problems that are interesting in equilibrium and even in non-equilibrium. For instance, recently we published a paper where we compute together with Stefano Lepri the flux of heat in a long-range system. It's an interesting problem. So there are really many problems, both in equilibrium and in non-equilibrium, for systems that are non-additive. I would like also to mention the series of papers that the first one is in the list of publications, is this paper with Ivan Latella, Perez Madrid, Alessandro Campa, and Lapo Casetti on the thermodynamics of non-additive system, because we have discovered a very interesting feature in equilibrium that in long-range system you can also let all quantities fluctuate. You can have equilibrium states even if energy, number, and volume fluctuate at the same time, while you cannot in short range. So this is another direction in which we are currently working. And of course, I have omitted all these issues of dynamics, quasi-stationary states, and so on, which of course would deserve a course by themselves. So if you want, I have concentrated on this issue, how hard it is to get microcanonical ensemble for these systems, and to also provide a set of examples where you can find ensemble in equivalence. Okay, so this is the end of my lecture. So I hope if there is some questions in the last 10 minutes.
Could you go back to your slides?
Sure.
The very first model that you discussed.
This one?
So here basically the way you sort of went to this auxiliary variable.
Yes.
How did you sort of remove the terms related to like sine theta I and sine theta?
Yes, okay. So you see here that you have cosine theta I minus theta j, okay? So then I write this as cosine theta I cosine theta j, okay? Plus sine theta I sine theta j. So then this is sum of so it's a square of the vector cosine theta I sine theta I, okay?
Yeah.
But then I can move all the angles in such a way that they align to the cosine, because the system is invariant under change of theta in theta plus alpha. But if you don't want to do it, in my review article, I also do the case both with the sine. And in the end, you will arrive at the same result. So if you have the sine, so let's do it with the sine so that you understand better. Okay. So if I do with the sine, so I have two auxiliary variables, Z1 and Z2, one for the sines and one for the cosines. Okay. So I will have here two terms, Z1 sum of cosine plus Z2 sum of cosine. Okay. Then the vector Z1, Z2, so I can write it as a scalar product. Okay. And so I have the modulus, which is this Z here, plus the angle. But the angle I can remove because I rotate the angles.
The other way of thinking about you mentioned is like by changing theta I by replacing theta I by pi, like by shifting all thetas by pi by 2, is it?
By an auxiliary angle, there can be any angle because I can rotate by any angle here, theta. It's invariant under any rotation. Ah, yes, it's pi. Yes, oh, you're right. Yes, because you want to eliminate the sign. Of course, yes. Anyway, in the review article, physics reports, there is the calculation with two auxiliary variables. So you see also the step, the intermediate step where you eliminate the sign and you get only one auxiliary variable. In these physics reports of 2009.
But the way you showed it last time, like in the last class, like you didn't get the Z, the auxiliary variable inside the integral, right?
No, for instance, this term here, Z dz, was not present, is not present, but you can, so in the end, this will not have an influence on the free energy or on the entropy. The auxiliary variable does not appear in the Curie-Weiss as an argument. It appears only in the exponential, Here it appears only in the argument, but it's not a problem. It's you can perform the integral with saddle point in the same way. In the large N will be the same. Other questions?
I mean, so you talked mostly of infinite range models. So for
Yeah.
so given in one dimension, there are no exact.
No, okay. So in one dimension, I showed the Kardashev. So now we are working in a model where you have, besides having nearest neighbor, so I have also next to nearest neighbor. Okay. And that's interesting because you are enlarging the size of the local interaction. We have published a paper already on in the canonical ensemble because the model was not solved in the canonical ensemble. So the solution is slightly more complicated. we have 7 regions in the phase diagram already in the canonical ensemble. So we are now solving the model in the microcanonical ensemble using the min-max method. But the number of parameters is huge, so we are fighting with the numerics to solve. So this is the direction, if you want, of saying, okay, I have the mean field term plus local terms. And then I increase the size of the local terms. It requires a lot of work, but okay. The other direction would be to take the 1 over r to the alpha. Okay. And the 1 over r to the alpha, there are really no result analytically, because it's a very tricky case. We have no definite results. So the matrix of interaction is a matrix that has some. So one thing that I can say, for instance, we solved with Shamik Gupta in a series of papers. We solved a problem which is related with the problem, which is a synchronization where the interaction of the rotors is decaying with the distance. In that case, we can solve. I still cannot believe that we can solve. The reason is that essentially this matrix is the interaction matrix is diagonalizable, is circulant matrix. So you can diagonalize it, and then you get going to the base where the matrix is diagonal. Then you can solve the problem in that base, and then go back to the original base, and then you can solve the problem. So for synchronization, we have obtained some results for decaying interactions. But for swing systems, it's really hard problem. So now we have also some renormalization group result. So of course, it would have been a totally different. So what we have done recently, you can find a PRL of Guido Giachetti, myself, and Nicolò De Fenu, and Andrea Trombettoni, where we succeeded to generalize the Berezinski-Kostelis-Tauler scheme for the XY model in 2 dimensions to a model where the interaction among the spins decay with distance. So we don't solve the model, of course, but we do a renormalization group. What we predict is that we predict that there is a phase with the breaking of order. So while in the XY model you have a quasi order in 2 dimensions, we predict that there is a region of order, so a magnetized region in that model. The numerics is not convincing, so I don't know if we are right. I hope we are right, but okay, the numerics there is no clear indication that there is this new phase in the XY model with long-range interactions. So we are trying sort of to turn around the real problem by considering problems where we can do some calculations. So synchronization, XY model, and so on. But it would be really very interesting to dispose of some general method to solve decaying interactions.
So I don't see any other questions. So maybe we.
Okay, so we can stop, and there will be tutorial in half an hour.
Thanks a lot for this really great setup.
No, thank you for the invitation. It was really very nice, and I hope that it will be possible to travel to very soon and reach your place. And my best regards to Jérémie Bec. I didn't see him, but I know him well. And to you, of course. So